For decades, we lived under the illusion that chips could keep shrinking and speeding up. Moore's law became a cultural myth. This idea suggested electrons would somehow keep cooperating indefinitely, as if physics itself were obligated to follow a corporate roadmap. But in reality, electrons didn't care about investor expectations. They followed thermodynamics. Slowly, then suddenly, we hit the ceiling. Today's chips run so hot that cooling systems are no longer just infrastructure. They're the primary machinery keeping everything alive. What's striking is how close we are to the edge, with modern processors often operating within 15 to 20 degrees Celsius of thermal destruction. This isn't engineering, it's cliffside driving. The industry focused on transistor density, but ignored the second half of Moore's insight. Switching energy per transistor needs to drop at the same pace. Without that, heat rises exponentially, and now it has. The public rarely sees this critical issue. When switching energy stops falling, each new generation of chips becomes hotter than the last. Because cooling systems can't scale exponentially, there's a hard limit to how much heat you can move per cubic meter. The entire architecture enters what many researchers now describe as meltdown behavior. It's a thermodynamic trap. If cooling falters for even a minute, the system collapses. This is why better cooling can't be the counterpoint forever. At some point, physics won't bend further. So instead of forcing electrons through narrow resistive channels, we move to computation that avoids resistive heating entirely. Light-based processors fundamentally change the equation. Photons don't experience electrical resistance, and they don't shed energy as heat when guided through optical pathways. So instead of pushing charged particles through a metal maze, you're shaping wave patterns in a transparent structure, more like guiding light through a resonant pathway than hammering electrons through silicon? Exactly, and it goes deeper. When you combine those optical pathways with quantum coherent structures, you create a substrate where information rides on resonance instead of friction. The system isn't fighting heat, it's avoiding the conditions that produce heat in the first place. It's like switching from dragging a crate across sand to floating it across water. The mode of transport changes the entire energy profile. And that's where ternary logic comes in. Yes, with 3 stable states instead of 2, each operation carries more information. That means you get higher information density without raising thermal output. You're not amplifying heat, you're amplifying meaning. So the electron era isn't ending because we lacked cleverness or desire. It's ending because the physics model that supported it finally reached its natural stopping point. The well ran dry. And the alternative isn't speculative or mystical. It's still physics, just physics that scales more gently. A shift from forcing electrons through resistance to guiding photons through coherence. From heat-limited to heat-lightened. And that's why the next era of computation won't be defined by pushing harder, but by choosing a substrate that doesn't push back.